Good day, students. Welcome to mathcoserve.com. In this clip, we're going to be going over a preview of calculus. We're going to be focusing on area and rate of change. If you have any questions at any point in time during this presentation, just feel free to post your question or comment in the comment section below, and we'll be glad to support you. Okay, so why calculus? In the examples we're going to be doing today, we're going to be determining if calculus can be used to find the exact results and if precalculus is sufficient to determine the exact result. Okay. The two main problems that calculus was designed to solve, or that resulted in the creation of calculus, has to do with the slope problem, or you can call it the slope of a tangent line. And the second problem is the area problem. All right. So when we're thinking about slope of a tangent line, there are different notations or names that you can use to refer to this. I'm going to be using rate of change, okay, just in the context of this problem to keep things easy. Now we can classify our functions into two categories when we're trying to find the slope of the tangent line or the rate of change. All right, so we have linear and nonlinear functions. So we have linear functions of this nature, basically straight lines, and nonlinear functions. Now, if you want to find a slope at any point in time on a linear function, you can use precalculus. Precalculus is sufficient to find the slope at any point in time of a linear function, okay? So precalc can help you find the exact slope or rate of change at any point, okay? So let's say I pick this point right here. Since this is a linear function, if I have any 2 points on this line, I can use m equals y2 minus y1 over x2 minus x1, and that will give me the exact slope. Or if I have y equals mx plus b, the equation of the line, m is basically what the slope is, okay, of any point on this line. Now, what if you have a nonlinear function? Okay, can you use this formula to find the slope at a point? The answer is no. So this is one big problem that resulted in the development of calculus. How do you calculate the slope at any point in time of a nonlinear function? Okay, so here calculus is needed to find the exact slope. Okay, if you want to use precalc here, you can use precalc to find the approximate slope or rate of change, but calculus is needed to find the exact slope. All right, and at some extremes, if you have a nice tangent line, for example, at the maximum and the minimum, you can have a horizontal line, which you could basically use precalc to find the slopes at those extreme values. But if you're looking at any arbitrary point, you want to quickly calculate the slope, you need calculus, okay? So let's say I pick this point right here, you have just one point. Okay, there isn't another point that's tangent to this curve that goes through this, that's collinear with this point. So if we want to find a slope here, we're basically looking for the slope of the tangent line, and that is where the derivative comes to play. Okay? All right, now another problem that we have to solve using calculus, or that resulted in the development of calculus, has to do with the area underneath a curve. All right, so what do I mean by area underneath the curve? So we have two functions here. So here, let's say we're going from 0 to 2, okay? And I want to find the area between this curve and the x-axis. So I want to find this area right here. Now, what you notice is that we have a basic geometric shape here, basic geometric figure. Now, what kind of shape is this? This is a trapezoid, okay? Now, anytime you're given a function and you determine the area between the function and the x-axis, and you end up with a geometric shape, it could be basic or composite. Anytime you end up with a geometric shape, guess what? Precalc is sufficient to find the exact area. okay? When we're talking about pre-calc, I mean, I'm including everything before geometry, trigonometry, algebra. Okay, so when you have a geometric shape, either basic or composite, you can use pre-calc to find the exact area underneath the curve. All right, so in this case, if you want to find the area here, it's not that hard. Just use the trapezoid formula, 1/2 sum of parallel lines, b1, b2 times the height. Okay, so this is b1, b2, that's the height right there. Now, what if you have something like this? The region bounded by the curve and the x-axis from 0 to 2, in this case, is a non-geometric shape. Okay, so which geometric shape or combination of basic geometric shapes can you combine to capture the exact area represented by this green region right here? You simply cannot. So this is what calculus helps you to do. Calculus can help you to find the exact area of regions like this that results in non-geometric shapes when they're bounded with the x-axis, okay? So this is a non-geometric shape. Okay, and if you want to find this area, is basically represented by the integral. All right, so the derivative helps you find the rate of change or slope of a function that's nonlinear, and the integral helps you find the area of a region that's not geometric. Okay, now one thing you want to keep in mind is that even though calculus was invented to solve problems like this that are unique, they can also be used to solve pre-calc problems, but they're an overkill, okay? If you can use pre-calc, it's much easier because sometimes calculus computations are more involved. So it's unnecessary or a waste of time to use them if you can simply use pre-calc and the prerequisites. Okay, so the questions that we're going to be solving are as follows. Instructions: determine if calculus is needed to solve the given problem or not. Find the exact answer when calculus is not needed and the approximate answer when it is. Okay? All right, so let's take a look at question number 1. It says a car is traveling at a constant velocity of v of t equals 30 miles per hour. How much distance does it cover in 2 hours? Okay, so in this problem, to help us determine if calculus is needed or not, let's take a look at the formula for distance, okay? So let's consider the formula real quick. So what is the formula for distance? Distance is the absolute value of velocity times time. Okay, you can think about this as an area scenario where the velocity is the height of the function and t is the time. Okay, so the velocity, what do you notice about the velocity? The velocity is constant. You have a constant rate of change. So since you have a constant rate of change here, when you're finding the distance, you do not need calculus. You could use calculus, but calculus is not needed here. Okay, so let's write down a note. Since we have a constant rate of change, calculus is not needed to find the exact distance. Okay, now let's connect it with what we talked about earlier. If I wanted to graph the scenario, if I want to give a graphical representation, okay, so we have time interval. Remember the time axis is the x-axis. So 1, 2, 3, 1, 1, 2, 3, 2. Okay, so this is a time interval. How would you graph the velocity? V of t is 30, so let's say this is 30 right here. It's just going to be constantly 30, right? So it's going to be a horizontal line. Bam. Now the distance is basically represented by the area between this line and the x-axis. Remember we talked about the area problem and how calculus helps us out? Do we need calculus here? Now check this out. What kind of shape do we have underneath the, the function and between the function and the x-axis. Is this a basic or a composite geometric shape, or is this a non-geometric shape? This is a geometric shape. It's a basic rectangle. Okay, so since we have a geometric shape here, we can use pre-calc. We do not need calculus. So let's find out what the exact distance is. Exact distance. All right. So we are using the formula D equals absolute value of V times T. The reason why I'm putting the absolute value here is because velocity is a vector. And when we're calculating distances, the sign is immaterial, okay? So the distance is going to be the absolute value of the velocity, 30, times the time, which is 2. Absolute value of 30 is 30 times 2, which is 60. And what is our unit here? So the unit for velocity is miles divided by hours, miles per hour. The unit for time is hours. So just cancel that out. And then you have 60 miles. Okay? So I knew you might have already known that the unit is miles, but I just want to show you how to calculate the correct units by making use of the units of the factors that result in the final result. Okay, so there goes the answer, 60 miles per hour for the exact distance covered by the car. Okay, now let's take a look at number 2. It says the particle's velocity is modeled by the function v of t equals sine pi t plus 2 miles per hour. Question, how much distance does it cover in 2 hours? So we knew before that distance is equal to velocity times time. Okay. If you take a look at this situation right here, our velocity function is not constant. Okay, so remember the velocity is our rate of change. Okay, rate of change, and rate of change can be thought of as a slope. Okay, so this is basically the graph of the slope. The slope is not constant. The distance is an area's problem if you're given the velocity. Okay, so what we're looking for in this problem is the area between this curve, this variable function right here, nonlinear function, and the x-axis. So what is this area right here? Is this a geometric figure? Is this a common geometric figure? The answer is no. So guess what? Calculus is needed in order to find the exact distance. Okay? All right, so let's go ahead and write that down since we have a variable rate of change or slope change. Calculus is needed to find the exact distance. Although at some points it's easy to use pre-calc, but if you want to find the exact distance at any over any interval, sorry, then you always have to use calculus to find the exact distance. Okay, now let's see. We are asked to find the approximate distance using find the approximate distance or the approximate result when calculus when pre-calc cannot give the exact answer. Okay, when only calculus gives you the exact answer. So let's go ahead and look for the approximate distance using pre-calc. All right. All right, so how do we find the approximate area underneath the curve? Well, we're going to be making use of rectangles. There are different shapes that can be used, but today we're just going to be making use of rectangles. So let's go ahead and sketch the rectangles on the following format. So no specific method was indicated, so this is just an approximation, okay? I'm going to be drawing my rectangles in such a way that the upper right vertex touches the graph, okay? And then what I'll be doing after drawing these rectangles is I'm going to be using the area of these rectangles to estimate what the area underneath the curve is, okay? So we're using geometry to estimate what the area of this curve is. So what we have is four basic geometric figures, four rectangles, okay? So that will give us an estimate of what the exact area is. So we have rectangle 1, 2, 3, and 4. So the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle 4 is an approximation of the exact area underneath the curve, okay? Which is basically the distance covered. So we know what the area of a rectangle is, the length times width. So for rectangle 1, 1/2 is the width times the length. Let's see. So we have 1/2 times 3 plus the second rectangle, 1/2 times 2 plus the third rectangle, 1/2 times the height is 1, and then the fourth rectangle, 1/2 times the height, which is 2. All right, so let's simplify this. We have 3 over 2 plus 1 plus 1/2 plus 1. Okay, these two 2's cancel out. So we have 4 over 2. When I combine 3 halves and 1/2 plus 2, 4 over 2 is 2. 2 plus 2 is 4. Okay? So what does this answer mean? Well, let's go ahead and contextualize our final result. The approximate total distance covered by the particle is 4 miles. Okay, we can only approximate if we don't have calculus available to us. So as we learn more about calculus, we're going to learn about how to find the exact distance by making use of a tool called integration. Okay, let's take a look at question 3. It says the position of a particle from the origin is given by the function s of t equals t to the fourth minus 2.5 t squared. Question, what is the rate of change of the particle's position at t equals 1/2? Okay, so we asked to find the rate of change. What on earth is that? What is the rate of change? The rate of change is the slope. Okay, we're looking for the slope at t equals 1/2, which is the same thing as the slope of the tangent line at t equals 1/2. Okay, now what do we know about this function that we're trying to find the slope at? This function is non-linear. Okay, so that means that the rate of change varies from point to point. So is calculus needed to find the exact rate of change? Absolutely. If you have a linear function, remember, then you don't need calculus. But if you have a function that's nonlinear, then you need calculus. Okay, so since we have a nonlinear function, let's write down a complete sentence. Since we have a nonlinear function, calculus is needed to find the exact rate of change. I'm gonna write RC, or slope. Okay. All right, but we're told in the initial instructions that if calculus cannot be used to find, if calculus is needed to find the exact answer, we should find the approximate answer using pre-calc, okay? So let's go ahead and find the approximate rate of change. Approximate rate of change using pre-calc, all right? So we're looking for the rate of change at t equals 1/2, 0.5 right here. So what we're going to do is we're going to draw a tangent line to the best of our ability and then find the slope of that tangent line, okay? So see, it's just draw a tangent line here. That's why we use an approximation here, because your tangent line could be perfect, sometimes it might not be perfect, okay? So that's why we have the estimation scenario. Now, what if you don't have a graph or a graphing calculator? How on earth are you going to be able to do it? It's going to be very difficult, okay? So that's why the graph is provided for you. But with calculus, you do not need a graph. If you have a function and you know the right calculus procedure, you can find the slope of the curve at this point without any problems whatsoever, okay? So we're going to be estimating the slope of this tangent line using our basic slope formula, rise over run. Okay, so I have two nice lattice points here that I'm going to be exploiting to find the slope of the tangent line. So let's make this into a line. Yeah. Okay, so these are the points I'm looking at. This point right here and this point right here. Bam. So I'm just going to use rise over run since it's faster. If you want to do y2 minus y1 over x2 minus x1, you get the same answer. So there goes my rise. I have a negative rise, and there goes my run. Bam. Okay, so the rate of change is going to be approximated using y2 minus y1 divided by x2 minus x1. Okay, so our y2 minus y1 is just a rise. If you drop it from 1.5 to negative 1.5, you have negative 1.5 minus 1.5. That's what the drop is, because this is going to be a y1 and that's a y2. And then when you run from, let's see where we're running from. If you're running from negative 0.5 to 1, x2 is 1 minus negative 0.5. Okay, let me just put in the coordinates just so no one gets confused. So we have 1.5, now switch it around. We have 0.5, negative 0.5, comma 1.5. That's your x1, y1. And then you have over here 1, comma negative 1.5. Sorry, the numbers are really small. It's hard to see. So this is negative 1.5 here, and that's 1. Okay, so there you go. And then if you carry out this calculation, you end up with negative 1.5 minus 1.5 is negative 3. 1 minus minus, slash and dash, that becomes a plus over 1.5. So we know that, well, let me show you how to do this. You can do that with your calculator by hand. You have negative 3 over 1.5 as an improper fraction is 3 over 2. And then you multiply the top by the reciprocal of the denominator, like that. And then your final answer will be cancel, cancel, negative 2. All right, so what does this answer mean? The approximate rate of change, the approximate rate of change of the particle's position is what? Is negative 2. All right, let's take a look at question number 4. It says, an object in flight is descending at a constant altitude. The distance of the object from the ground is given by h of x equals negative 43x, where x and h of x are measured in meters. What is the rate of change of the altitude of the object? Let's put it at x equals 2, okay? All right, so now we are finding the rate of change. Let's see, rate of change. Now, what does rate of change mean again? Rate of change is your slope, okay? Slope, or the slope of the tangent line. Now, take a look at this function right here for a second. We're looking for the rate of change of this function. Do we have a constant rate of change or a variable rate of change? If I were to graph this function, what will it look like? Is it going to be a linear function or is it going to be a nonlinear function? We can clearly see that this is a linear function because it's in the form y equals mx plus b. All right, it's a first degree function, so if you have it in this format, then it's a straight line. So that means you have a constant rate of change. All right, so is calculus necessary here when you have a linear function with a constant rate of change? The answer is no. You can use pre-calc to find the rate of change. All right, so let's write down the remark. Since the rate of change, since the function is linear, the function is linear, calculus is not needed. Is not needed to find the exact rate of change. Find the exact rate of change. All right, so let's go ahead and find the exact rate of change. Exact rate of change. So what is the exact rate of change here? If you have a function, h of x equals negative 43x, what is the rate of change? What is another word for rate of change? Another word for rate of change is the slope. So if I gave you a line with equation y equals mx plus b, can you find the slope or the rate of change? Absolutely. The coefficient of x is your slope, right? So in this scenario, that's exactly the same thing, okay? Your slope is the coefficient of x, which is negative 43. So guess what? That is your rate of change. So the exact rate of change, the rate of change of the object, at x equals 2 is negative 43. Okay, now guess what? Since the rate of change is constant, it doesn't matter where you're at, you will always get the same thing. Okay, that's what happens when you have a linear function. All right, let's take a look at question number 5. It says use rectangles in the graph below to find the area bounded by y equals 3 over x, this function right here, x equals 0.5, x equals 2.5, and the x-axis, okay? So this is an example where we're using pre-calc, again, to estimate what the calculus result is. What calculus can help us do in this problem is to find the exact area of this region right here. If you notice, this region is a non-geometric shape. You can't think of a geometric shape that captures this perfectly or even a combination of geometric shapes, okay? So you need calculus to find the exact area. But since we haven't studied the tools yet, we are going to have to estimate with what we know. So that's why we have these rectangles provided for us, okay? So let's go ahead and compute the approximate area. So we have, let's write it down, approximate area. Let's see. The formula that we're using here is your basic geometry formula, which is area of a rectangle is length times width. Okay, so we have rectangle 1, 2, 3, 4. So we're just gonna have the area is gonna be the area of rectangle 1 plus the area of rectangle 2 plus the area of rectangle 3 plus the area of rectangle number 4. Okay, so that will help us find approximate the area between this curve, the boundary lines, 0.5 and 2.5, and the x-axis. All right, so let's start with triangle 1. What is the area? So the width is 1/2 times a height of 5.5. So 1/2 times 5.5 as a fraction, 11 over 2, plus area of the second rectangle, 1/2 times 3 area of the third rectangle, the width is always 1/2, times the height of the third rectangle is 2, 1/2 times 2, and then the area of the fourth rectangle, the width is 1/2, and the height is 1.5 or 3/2. All right, so let's go ahead and simplify this. So I have, or if you want to use a shortcut, you can factor out all the 1/2s, combine the numbers, and then you can multiply. Or you can just multiply these by the LCD and then combine them, whichever method you like to use. So let me just multiply. So I have 11/4 plus 3/2 plus, let me just as a fraction, 2/2 plus, this is 3/4. And then you want all the denominators to be the LCD of 2 and 4, which is 4. So I'll simply double the fractions with 2 in the denominator. Okay, and then we're going to have 11/4 plus 6/4 plus 4/4 plus 3/4. Okay, 6 plus 4 is 10, 11 plus 3 is 14. So 10 plus 14, we have 24/4. And just divide, and our final answer is 6. Okay, so that's the approximate area between this curve, the boundary lines 0.5 and 2.5, and the x-axis. Okay, so that's that. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful to you, do give us a thumbs up. Your positive feedback is very important to us. As indicated earlier, if you have any comments or questions about the material we just covered, just place it in the comment section below, and we'll be more than glad to support you. Don't forget to subscribe to our channel for updates to other cool tutorials such as this. More clips can be found on math.serve.com. Thanks again for watching, and have a wonderful day.